Good morning, everybody. This is the last part of this electrochemical energy sources series in 6.2 physical chemistry part, and in the syllabus of 6.2 physical chemistry 6.2 paper physical chemistry part, this is the second chapter under the heading electrochemical energy sources. So here in this chapter, electrochemical energy sources, we have to discuss about the primary cell, that is dry cell. In secondary cells, some examples of lead storage battery and nickel cadmium battery, and third one is fuel cells. So these things we have to in detail study about these things in electrochemical energy sources. In these electrochemical energy sources, that means the definition of this electrochemical energy sources, you can define it as a battery. Electrochemical energy source is nothing but a battery. A battery is a combination of many electrochemical cells connected in series. Any redox reaction occurring at an appropriate electrode can be employed to generate electricity in such cells. The main features of a good battery are it should be light to carry, that means it should carry light weight there, and it should provide power for longer time, and it should be capable of being recharged, and as usual it should be cheaper, economically viable for the usage of common man, and it should have a constant voltage, and it should be long laster. So these are the main features of a good battery there. So such type of batteries are in use there in our normal life, and we can discuss about one by one. First one is dry cell, and it is also called as primary cell. And these dry cells are not rechargeable. Once we use it, and it will be exhausted and it will be spoiled off. We have to use another one. That cannot be rechargeable there. Those cells are called as primary cells, which are non-rechargeable. So in an example for this dry cell, we have taken it here. The diagram of that dry cell has been mentioned it here at the left hand side, and at the right hand side you can see the labeled diagram of the dry cell, that is primary cell there. It consists of a zinc metal container which is acting as an anode, filled with moist paste of ammonium chloride and Zn chloride, and containing a graphite cathode surrounded by MnO2. You can refer to the diagram there. We have pitch seal, zinc container acting as anode, graphite which is acting as a cathode which is at the center, and by the side of it we have MnO2 plus C coating, and by the side of it we have porous paper lining, and completely the cell has been filled with a moist paste of ammonium chloride and zinc chloride. That is a labeled diagram of dry cell, that is primary cell. The complex electrode reactions may be approximately represented as represented the equation there. At cathode, NH4 plus MnO2 plus electron giving rise to MnOOH plus NH3. That is reduction taking place at cathode, accepting the electrons. And as usual at anode, zinc is the anode there, and it undergoes oxidation to give rise to Zn2 plus 2 electrons. So electrons have been released there. So at zinc anode, oxidation takes place, and at MnO2 plus C, where it is there, we are considering that graphite rod, there reduction takes place there. So Mn4 plus is reduced to Mn3 plus at the cathode, and ammonia is produced as a product. And this gas ammonia combines with Zn2 plus ions to form a complex ion of ZnNH3 4 times 2 plus. As such, no pressure of the gas is developed inside the cell. So it forms a complex ion. Therefore, ammonia gas is not released. The released gas has been combined with Zn2 plus ions, forming a complex ion ZnNH3 4 times 2 plus. However, due to acidic nature of ammonium chloride, due to hydrolysis, the zinc metal is constantly corroded. Due to this, the cell does not work for a longer time, and its voltage is approximately 1.25 volts to 1.5 volts. So this is a typical dry cell, primary cell, and its parts have been mentioned there. what are the equations taking place at anode and cathode has been mentioned, and how much of potential it is going to develop, and that has been mentioned as 1.25 volts to 1.5 volts for each dry cell. If you want more voltage, you have to connect these number of dry cells in series so that you can get more voltage. Suppose for one cell it is 1.5 volts, means if you want 3 volts means you have to connect 2 cells in series, just like as we are using it in our torches there. We use these dry cells, Eveready batteries, Nipo batteries are there, no? Those are all the examples of dry cell. This is a primary cell and this cannot be recharged. So once it is over and it has been exhausted and it has been spoiled, and we have to throw it out and we have to use newer one. This cannot be recharged. That's why it is called as a primary cell. Another type of cells are there, secondary cells. They are called as secondary cells and they can be rechargeable. These cells are called as secondary cells because they are rechargeable. Once the batteries have been exhausted, again you can connect it to the external source of EMF, or you can connect it to the external battery and you can recharge it. Connect it to the electrical socket and you can recharge it there. Those cells are called as secondary cells. As far as our syllabus is concerned, there are 2 examples you have to discuss about these secondary cells there. First one is lead storage cell, another one is nickel cadmium storage cell. Lead storage cell, it consists of a lead cathode and a grid of lead packed with PbO2 as anode. The electrolyte is sulfuric acid and the half cell reactions are, it has been mentioned there, PbO2 solid plus SO4 2 minus plus 4H plus 2 electrons, giving rise to PbSO4 solid plus 2H2O. This reaction is taking place at cathode because we are observing that electrons have been accepted there. Then at anode, PbS plus SO4 2 minus, giving rise to PbSO4 solid plus 2 electrons. So at anode, oxidation takes place, so electrons have been released. So each cell contains a number of such cathode and anode plates, and there are 3 to 6 such cells are joined in series to form 6 to 12 volt battery. So that's how, if you want more voltage, you have to connect more number of plates so that more reaction takes place and more potential will be developed there. And once a battery has been constructed, you are using it as it is, and when it has been exhausted, again you connect it to the external source, again that can be chargeable there. So these reactions will be reversed. At cathode, the reaction will be reversed, that it becomes an anode, and at anode, the reaction will be reversed and it becomes cathode there. So earlier oxidation, while charging, it becomes reduction, and earlier reduction, while charging, it becomes oxidation there. So that's how it is a rechargeable battery. The electrode reactions in it can be reversed by passing an external current through it, and thus the battery can be recharged. That's why by connecting it to the external source there, you can reverse the reactions at anode and cathode so that the chemicals can be regained. So that again when you disconnect it from the external source, again the battery starts working as in the case of those 2 equations there. That's how it is a rechargeable battery. The second example for this secondary cell, that is nickel cadmium storage cell. It has a longer life than storage battery, but it is more expensive there because of the expensive metals we are going to use it there. That's why the battery itself is more expensive. The half cell reactions have been mentioned there. It is NiO2 solid plus 2H2O plus 2 electrons, giving rise to NiOH twice plus 2OH minus. This is the reaction taking place at cathode because you see that their electrons have been accepted. So reduction takes place there. And at anode, cadmium solid CdS plus 2OH minus, giving rise to CdOH twice plus 2 electrons. This is the reaction taking place at anode. And each cell has an EMF of approximately 1.4 volts. So if you want more voltage, then you have to connect such type of nickel cadmium storage cells in series. So that depending upon the usage there, you can connect them in series and use them. So the comparison between this lead storage cell and nickel cadmium storage cell is comparatively nickel cadmium storage cell is slightly expensive because of the nature of the metals we are going to use it here, nickel and cadmium being costliest metals there. That's why construction requires more amount. That's why these batteries are more expensive than our normal lead storage cell. The third type of electrochemical energy sources mentioned in our syllabus are fuel cells. And in these fuel cells, only one example we have to deal it in discuss in detail, that is hydrogen oxygen fuel cells. Then we shall understand what is this fuel cell and what are these fuel cells then. A compact source of power produced from fuels is called a fuel cell. Here, fuel is not burnt as in generators or boilers. These cells serve as a pollution-free source of power. The fuel cells are being employed in spacecrafts. The main difference between a conventional electrochemical cell and a fuel cell is that in a fuel cell, the materials undergoing oxidation at anode and reduction at cathode are stored outside the cell. These are not the part of the cells as in dry cell. So this is diagrammatic representation of hydrogen oxygen fuel cell. You can see a labeled diagram of hydrogen oxygen fuel cell. This is hydrogen oxygen fuel cell. The general design, it has been mentioned there. In this cell, the cell consists of two electrodes made of perforated carbon. Platinum is coated on the surface of electrodes to act as a catalyst. The electrodes are placed in an aqueous solution of sodium hydroxide or KOH. Hydrogen and oxygen are bubbled into the cell under a pressure of 50 atmospheres. When the electrodes are connected, a flow of electric current takes place. And the cell representation, we can represent it as hydrogen at cathode bar KOH or NaOH bar oxygen at cathode. It is both are perforated carbons there at anode and at cathode. At anode hydrogen and at cathode oxygen gas there. During operation of this cell, the following electrode reactions are taking place. At anode, 2H2 plus 4OH minus giving rise to 4H2O plus 4 electrons. You can observe here it is an oxidation reaction because electrons have been released there. And at the same time at cathode, oxygen plus 2H2O plus 4 electrons giving rise to 4OH minus. Here you can observe that here electrons have been accepted, that's why reduction reaction has been taken place and it is taking place at cathode. Therefore, the overall cell reaction is 2H2 plus O2 giving rise to 2H2O liquid. And EMF of the cell is found to be 1.229 volts and it does not depend on the composition of the electrolyte. It depends upon only the oxidation reaction taking place at anode and reduction reaction which has been taking place at cathode. During the discharge of this hydrogen oxygen fuel cell, the voltage is within 0.7 to 0.9 volts depending on the density of the discharge current on the electrodes. And in the best design of the cell, the current density reaches up to a maximum of 200 to 300 milliamperes per centimeter cube, per centimeter square. And the importance of this hydrogen oxygen fuel cells, such cells are used in spacecrafts. The electrolyte used in these cells is an ion exchange material and not a solution of sodium hydroxide or KOH. This ion exchange material is used in the form of a membrane. A membrane allows easily to flow of protons which react with oxygen and electrons to form H2O. The hydrogen oxygen fuel cell used in spacecraft is shown in the diagram. So instead of NaOH or KOH in the middle of the diagram there, instead we have ion exchange membrane here. You can see that. And at the left hand side we are pumping in that hydrogen gas and at the right hand side we are pumping in that oxygen gas there. The same type of reactions will take place, only the difference is in this ion exchange membrane has been used instead of that alkali there. So that here no leakage will be there and the potential developed here in this, it will be a constant one and it can be used for a longer time. Constant production of potential has been taken place. So depending upon the output there, how much of potential we are going to require it, we are going to connect such type of small ion exchange membranes in these fuel cells there in series, and you can get how much of potential we require in that case there. So this is a simple case of hydrogen oxygen fuel cell. And usually the applications of these hydrogen oxygen fuel cells they are used in spacecrafts there. And so normal reaction it has been taken place in such type of fuel cells. Half S2 giving rise to 2H plus 2 electron. It is at anode, oxidation takes place, and as usual at reduction takes place at cathode, that is 2H plus O2 plus 2 electrons giving rise to H2O there. So this is a simple case of hydrogen oxygen fuel cell which is used in spacecrafts. And that completes the syllabus, this chapter, electrochemical energy sources, the second chapter in the physical chemistry part of 6.2 paper, and the complete electrochemical phenomenon, the electrochemical cells in part 5, and sixth part is electrochemical energy sources. Therefore, the complete syllabus of this VSKUB 6.2 chemistry paper, physical chemistry part, it has been dealt in 6 parts there. So students, if you are having any doubts there, you can clarify it by just ringing to me to my personal number, or you can contact by my email ID, that is govindarajb1964@gmail.com. So by email also you can contact and you can clarify the doubts. Thank you very much for your patience hearing.